Everyone, good evening. In our previous session, last week, we have started with this particular UART based LED controller, and we have basically discussed about the idea, the project idea, like what exactly we are going to implement. And we have basically discussed about our UART protocol, like how the protocol frame is going to look like, what are the different kind of bits we are going to have, and how to basically start a particular frame, and how to and when we are going to send the data parity and stop it. We have discussed about the transfer of UART protocol and how our particular project is going to look like and what exactly we are basically implementing, and all we have discussed in great detail. Once let me brush up all the particular things so that it will be clear and you can maintain your continuity, right? Now, over here we have basically discussed about the project overview, like exactly what are we going to do. And we have seen that we are going to have a host PC where it is going to send a single byte serial commands. So if you haven't the previous recording, I recommend you to watch that first, so that in our previous session we have basically introduced entirely about our project, and we have discussed entirely about our project. This is second session of our UART based LED controller session. Okay. Yeah. So, anyways, let me brush up so that it will be more clear. Like you can maintain the continuity and all. Right now, so basically, we have seen that the very project overview is basically we are going to have a host PC which is going to send a single byte serial commands over UART, and the FPGA is going to receive them, decode them, and converts that particular command into a PWM signal that it is going to control our LED brightness. That is our entire overview of the project, but in great detail we have discussed in the previous sessions, right? Now, we are going to, what we are going to have is we are going to receive a particular serial data using our FPGA. We are going to receive a serial particular data where I'm going to have a 9600 baud rate, and I'm going to have 8 and 1 framing. 8 and 1 framing is nothing but 8 bits of data, no parity, and one stop it, and no external UART IC I'm going to use for this. And I'm going to decode those particular commands, and I'm going to generate the PWM signals so that my particular LED is going to be work. And this is what I'm going to do. And the future work, if you are going to have any particular FPGA board, you can basically implement it on it your FPGA board. Okay. Now, so this is what we have seen in our previous sessions also. Like if the user is going to basically on or off the particular button, or if he is going to drag a brightness, UI is going to basically, you know, uh, uh, interact with the script, Tinker script, and it is going to be converted into the commands into the USB, and USB it is going to send to the UART bridge chip. In the Nexus FPGA in the previous session, I have shown you, right? So in a Nexus FPGA, that particular bridge is going to convert that into UART commands, and our FPGA is going to receive them, and we are going to decode them. Okay. So that is what we have seen in our previous session also. So this is how a particular Tinker script is going to look like. So if the user, let me show you one more time so that it will be more clear. Yeah, this is what I was talking about in the previous session also. So here the user is going to select the LED 1 or LED 0, and he is going to select fade or blink. And here we can basically increase the brightness of my LED or decrease the brightness of my LED. So whatever the user is going to play with this particular UI, that will be converted into the script. Okay, so that will be converted into script, and this particular script it is going to convert this into the information, byte information. So basically, this particular software is going to detect whatever the events which are going to happen in the UI level, and it is going to call back the Python code. And Python code, it is going to construct a byte. It is going to construct a byte, and using this py serial, it is going to write down that particular byte, and that particular byte of data will be sent towards the USB bridge, and that will be converted by the bridge. Okay, so this is what we have seen in our previous sessions also. So this is what I was talking about. So my PC terminal is going to give it to the UART receiver. And here we are going to have a particular bridge which is going to convert this particular commands into my UART commands and UART receiver. This is what we are going to implement it now. Okay. And first one is UART RX. So this is what we are going to implement in this particular session. UART RX command decoder, LED controller, top module. And in future, we can try working on this particular things. But in this particular session, we are going to look into development of this particular four modules. So UART RX is going to sample the serial line and it is reconstructing the bytes and it is also going to flag the completion. And command decoder, it is going to basically trying to understand whatever the data it has received, what is the meaning of that particular data. If the user has sent any particular data, it is trying to understand what exactly the user wants to say. Okay, that is what the command decoder is going to do. And it is going to decode what user wants to say and it is going to give it to my LED controller. So LED controller, after receiving the commands from my command decoder, it is going to give it to your LED controller. So LED controller, it is going to control the LEDs. That is what we are going to develop. Okay. Now, so this was about your UART-RX. This, anyways, we are going to discuss LED controller. We are going to discuss, and this and all the USB is connected directly to the FPGA or what, and what are the different kind of constraints file we should have when we are going to implement it on a physical FPGA. That and all we will discuss. First, let us try to understand the code, right? Now, first of all, before going to understand the coding and all, we need to understand one more thing over here. One second. So we need to understand the command format over here. So without understanding the command format, we cannot able to, build this particular project. So what is this command format is? So the whatever the Python script the user is going to send, right? He is going to basically send me 8 bits of data. Okay. Now in this particular 8 bits of data, my hardware, the UART receiver, it is going to receive basically 8 bits of data. Now in this particular 8 bits of data, the first two bits are B7 and B6. This is going to basically select what kind of command it is. Whatever the 8 bits we are going to receive, right? Using our UART RX. So this is my software. Software is going to send me the 8 bits of data via the USB. So USB to UART converter bridge, it is going to convert this USB commands into UART command and my UART RX is going to receive it. In our previous session also, we have discussed this in great detail, right? Now, after UART RX, it is going to receive 8 bits of data. We need to know what is the meaning of this particular 8 bits of data, right? Now, so in this particular 8 bits of data, the first 2 bits are going to tell me the what kind of command it is. So if my first 2 bits are equal to 00, then it is nothing but a brightness command. For adjusting my brightness, if I want to adjust the brightness of a LED, the user is first of all going to give the two MSB bits as 00. And if the user wants to select a particular LED, he is going to give the command as 01. And let's say if we want to adjust the mode, that means only static in the sense LED is not at all changing, fade in the sense LED is glowing and LED is diminishing, and next is blinking in the sense we know already. So we have different kind of modes, and if I want to set the mode, the MSB which should be 10, and 11 is not used for any particular thing, it is reserved for future uses. Okay, so if I want to basically adjust the LED, or if I want to choose out of 4 LEDs, if I want to select a second LED, okay, before going to choose that particular LED, you need to give the command 01 so that the hardware will come to know that, okay, user wants to choose a LED. Now, let's say if the user wants to adjust the brightness of the LED, what he should do, he should basically give the MSB bytes to be 00. That means the hardware will come to know that, okay, the user wants to adjust the brightness. So depending upon what kind of MSB bits I'm going to provide, the hardware is going to come to know that, okay, the user wants to play with this, or this is the kind of command it is going, he want to adjust. Okay. So this is what we are going to do. Now, next, let's say suppose if I want to adjust the brightness. Okay. So first up, what should I do? I should update the MSB bits to 00. So first I'm going to update my MSB bits to 00. Next, how many bits are remaining? Next, 6 bits are remaining. Okay. First of all, tell me, is my voice clear? My voice is clear, right? Okay. Thanks for letting me know. Now, so first of all, what we are going to do, let's say if I want to adjust the brightness, okay. So in the software, what I'm going to do is I'm going to provide the first 2 bits, that is my MSB bits to 00. Okay. Now, The remaining payload bits, the remaining 6 bits are going to be my information. What information? In this particular case, it is brightness information because my first 2 bits are 00, right? So this 6 bits now are the brightness information. Now, using 6 bits, how many values we can represent? We can basically represent from 0 to 63. Okay. Now, if I want to, if we have observed in the previous session, we have basically have the brightness values from 0 to 255. Okay. For having 0 to 255, 6 bits are not 6 bits are not sufficient. Okay. If you are going to have only 6 bits of data, 1, 2, 3, 4, 5, 6 bits, you have only 6 bits of data. Using this 6 bits of data, you can represent from 0 to 63 only. Okay. But if you want to represent the brightness values from 0 to 255, normally the pixel values will be from 0 to 255, right? That's the reason here they have written 0 to 255, but you cannot represent up to 255 because you have only 6 bits of data with you. Okay. Now you can simply say, sir, we can basically increase the payload size. What's the matter in that? But remember, we are dealing with UART. Okay, the maximum payload length can be 5 to 8 bits. That's it. Okay, here we are going to have 8 bits of data. This is my UART frame. The software is sending the UART frame, and out of this particular 8 bits of data, first 2 bits are reserved for deciding your mode. Okay, now we have only 6 bits for representing my brightness. Okay. Out of 6 bits, you can use it for deciding you can basically represent up to 63 only. Now, what is that we are going to do? We are basically multiplying it by 4. That's it. For representing to 255, we are basically multiplying it by 4. Let's say suppose if my brightness value is 63, I'm going to multiply it by 4. So what's 63 into 4? Okay, let me open the calculator quickly. Approximately 252. So let's say if my value is equal to 63, then I'm multiplying it by 4. That means I'm reaching up to 252. I cannot reach up to 255, but using 6 bits, what I'm going to do is I'm reaching up to 252 value. Okay, this is what I'm going to do. Now, next is LED. Let's say suppose if I want to select a particular LED. Now, what is the user going to do? He is going to create a byte or a frame. So let's say if we want to select a particular LED as 0, if we have, let's say, 4 LEDs, LED 0, LED 1, LED 2, and LED 3. Let's say if the user wants to select LED 0. Now, first, what he should do, he should configure the first 2 bits as 0, 1. Okay. Then he should provide which particular LED he want to select. So what we are going to do for selecting 4 LEDs, what we are going to do is we are going to basically have 3-bit. Okay, 3-bit means we have total 7 LEDs. So 0 to LED 7. So basically we have total 7 LEDs, and for representing my 7 LEDs, I'm going to use 3 bits of data. Now, let's say suppose user wants to select LED 0. Now what he is going to do, first of all, he is going to provide the MSB bit as 01. Next, he is going to give the payload as 0, 0, 0. That means the hardware will come to know that, okay, user wants to select LED 0. Let's say suppose if the user wants to select LED 7, then my 3 bits should be equal to 1, 1, 1, 1. This is how my user is going to basically frame. Okay. This is how he is going to create a frame. Okay. Let me show you one more example. If this is my PC I'm going to have, and via this PC, I'm going to have the USB interface, and this is my FPGA. And in this FPGA, I'm going to have the USB interface, and this is my FPGA I'm going to have. And from this, I'm going to have a bridge. So this bridge, it is going to convert this USB signals into my UART signals. And here we are going to develop our UART receiver. This receiver is going to receive this UART signals. Okay. Now, what is that PC? The software is going to do, it is going to send me 8 bits of data. Okay. So in the software level, what we are going to do, we are going to create this particular frame. If I want to select the brightness, my MSB bits will be equal to 00. and what kind of brightness I need to have, I'm going to basically decide it. So using the 6 bits, I'm going to decide it. Let's say suppose if I want to have the brightness to be entirely zero, I'm going to send all the particular bits to be all zeros. 1, 2, 3, 4, 5, 6 bits to be equal to zero. Let's say if I want to have the brightness of 4, then I'm going to have 0, 0, 0, 0, 0, 1. This is how I'm going to send the frame. Now, let's say if I want to select a particular LED, then what I'm going to do, my MSB bits will be equal to 0, 1, and LED value, if I want to have LED 1, then I'm going to provide 0, 0, 0, and how many bits I'm going to use? I'm only going to use 3 bits. So 3 bits is nothing but 0, 0, 1. So this is the information which I'm going to send it from the PC to the USB to the bridge, and RX it is going to receive the frame. Okay. Here RX is not going to know what is the meaning of this particular data. It doesn't know anything. It is going to forward it to something known as command decoder. Okay. We have seen here, right? Let me show you again. So Rx it is going to receive that particular data and it is going to pass it to the decoder. Decoder duty is to try to decode what is that particular information it has received. It is going to decode what is this information. It does the user wants to select the LED or does the user wants to have the brightness or what user wants. Decoder is going to decode. Okay, this is what I'm going to do. Okay, now so this is my byte information which I'm going to have. Is it clear up to here? How user is going to create a frame? Is it clear? Great. Now, so this is one example where we have where we can see of configuring one LED. So I'm going to have type is equal to 0, 1 and payload. I'm going to decide for LED 2. I'm going to give this particular information. That is, my program is going to sell me hexadecimal 42. Okay. Now, if I want to select the mode, I'm going to have type is equal to 10. Then payload is equal to this is my mode. Okay, which is nothing but my static. For static, I'm going to have all zeros. And if I want to select the brightness, I'm going, for example, 50% brightness, I'm going to send this particular information to 0. Okay. So this is how I'm going to basically send my particular byte of information. Okay. Now, the major question over here is how we are going to basically configure an LED. Okay. So in this particular example, if I want to configure one LED, first of all, in step number 1, I'm going to send 8 bits of data. And next, after this, after sending this byte of information, I'm going to send next 8 bits of information for setting the mode. And next 8 bits of information are setting for my brightness. I cannot configure LED selection, mode selection, and brightness selection at the same time. Basically, I'm going to send 3 bytes of data for selecting this particular 3 configurations. This is what my design is. Okay. So if you want to select a particular LED, you send a byte of data. If you want to configure a mode, you send a byte of data. If you want to select the brightness, you send a byte of data. So whatever the configuration you want to do, you are going to send that many number of bytes of data. Okay. So this is what I'm going to send. Yeah. So if you want to check it out in your scripting, this is how it is going to look like. So serial dot port baud rate bit size, and we are going to send this bits of data like this. We are not going to focus upon more on software configuration. We are going to deal in the hardware level itself. Now, so let us try to develop our UART RX file. So this receiver is going to receive the data, that is my transmitting data, whatever the bridge it is going to transmit, right? It is going to receive. Now, basically, bridge is following the configuration of 9600 baud rate. And in our previous sessions, we have discussed it that for 9600 baud rate, I'm going to have 104 microsecond. Okay. Now, first of all, let me open the UART receiver file. Yes. So this is my UART receiver file where I'm going to have clock, reset, and one signal which is known as baud underscore tick. So what is this baud underscore tick? We will discuss. And next is RX underscore serial. So this is what the pin I'm going to use for receiving the serial data. Now, whatever the serial data have received, From the bridge, I'm going to convert it into a parallel data. So whatever the serial data I've received, right, that I'm going to convert it into parallel data and I'm going to give to the decoder. So for the decoder, I'm not going to give the serial data. I'm going to convert it into a parallel data and this parallel data will be given to my decoder, okay, which is of 8 bits. Now, how to convert it into parallel also we will see. And next is Rx underscore done. That means I have completed entire serial to parallel conversion. Okay. Now, next I'm going to have different kind of states. One is idle, start, data, stop, and cleanup. Okay. And I'm going to have different parameters. One is state, tick underscore count, bit underscore index, and Rx underscore byte. I will let you know what is this and all. Now, and I'm also going to have a kind of synchronizer, two-stage synchronizer. This you can use or you can skip it. It's not a problem. So generally, all the particular bits of data is synchronous to clock anyways in your FPGA. So this is not an required step. So let's see from here. This is my FSM logic which I'm going to write down. So if I'm going to reset, by default, my state will be in idle and tick underscore count will be equal to 0 and bit underscore index will be equal to 0 and Rx done is 0 and Rx data is also equal to 0. Now, in the idle state, my tick underscore count will be equal to 0, bit index is equal to 0, and whatever the data which I'm going to have, if it is equal to 0, then I'm going to start state. Okay, because in your UART, start of a UART frame is going to indicate when your start bit, if it is equal to 0, then only you're going to the next state, right? So now you have entered into start state. For example, let's remove this particular Baud underscore tick and tick underscore count for a moment. Let's say if I'm removing this Baud underscore tick, let's assume this particular state is running for the passage of clock. Then what is going to happen? For every passage of clock, this tick underscore count will be incrementing. So let me visualize over here. So this will be my clock. And I have written this particular logic in with respect to clock itself. Okay, always at the rate passage of clock. The key statement I have written over here only. The next state logic I have basically written in with respect to my clock itself. And what I'm going to do over here, I'm basically checking for my tick underscore count. If it is equal to 7, okay, let me remove this one also. Tick underscore count also, let me remove it. One second. Let me remove everything and let us try to understand what is happening over here. Yes. Um, 1 second. Let me remove this. I wanted to explain something. So I'm removing uh, the stuff. Okay, let me write it down over here. So let's say if I'm going to have the start state, if I've entered into start state and I've already detected the start bit, I can simply write down next underscore state is equal to data. This is what I can write down simply. Okay. So in my start state, from idle state, I'm entering into start state. This is my idle state. And from this idle state, I'm entered into start state. When I have entered into start state, whenever my received bit, that is TX, if it is equal to 0, I've entered into start state. Okay. Now in the start state, I can simply write down next state is equal to data. But I'm not writing that because here I should wait basically for 104 microsecond because each particular bit is holding for 104 microsecond. That means each particular bit is available for 5208 seconds. This all calculations we have done in our previous sessions. If you haven't watched that particular session, I recommend you to watch that. So in our previous session, what we have seen that each particular bit is basically available for 5208 seconds. Now, if we are, that means the start bit will be available for 5208 cycles, and data bit, that is first bit, will be available for 5208 cycles, and D2 will be available for 5208 cycles. Like this, up to D7, the bits will be available for this much duration of time. Now, we have basically sampled our start bit. Okay, we have basically detected our start bit and we have entered into our start state. Now, in the start state, we cannot immediately jump into data state. This particular start state should stay for how many number of cycles? 5208 cycles. I should stay over in this cycle only. in this state only I should stay. Okay. Is it clear, guys? What is your question, Karthik? How do you write this code by using a circuit? Which circuit you're talking about? Okay. So I was saying about in the previous session, we have seen that each particular data is available for 5208 cycles that we have seen in our previous session, right? Now, I have detected a start state and I have detected a start bit and I have entered into start state. Now, I should stay in the start state for 5208 cycles because my start bit will be up to that many cycles. I'm not going to get the data up to 5208 cycles. Okay. Now, for that, what I'm going to do further, I should basically implement a counter, and my counter should count for 5208 seconds. Then only I should change to my data state. Am I clear? Yes or no? So I should basically design a counter. That counter should basically count for 5208 cycles, and then only it should go to the data state. So up to that many number of cycles, you're not going to get any data. Okay. Now, for that, I need to develop a counter, and where I'm going to develop that particular counter, that I'm going to show you now. So that is nothing but my Baud generator model. So here I'm going to have the clock frequency as 10 megahertz, and I'm going to have the baud rate as 9600 and the clock and reset. So previously we have took 50 megahertz, so I'm going to have 5200 cycles. Depending upon the clock frequency, it is going to change. So in this particular model, the baud rate generator model, I'm going to have clock, reset, tick. Output is my tick. Now, so I'm going to have a count, and if reset, my count will be equal to 0. If count is equal to divisor minus 1, that means if it is reaching that many number of cycles, in our example, it is 5200 cycles. So if I have reached that particular count, then tick is equal to 1, else tick is equal to 0. That means what I'm going to do over here, which code you're talking about, baud rate or FSM? Uh, have you have you attended the previous session, the baud rate generation module and the TXFSM design? Okay, please attend that particular session so that this will be clear, like what exactly I'm discussing, right? So that is what I have entered from idle state to my start state whenever my start bit is equal to 0. So whenever my input if it is equal to 0, that means it's a start condition, and I have entered into this particular start state. Now I should wait in this particular start state for 5200 some 5400 cycles because your 5208 cycles because your next data is not available up to this many number of cycles. So how to wait in this particular state only? You are going to implement a counter. Okay, that particular counter logic we have implemented over here, which is nothing but my baud rate generator model. So in the baud rate generator model, where is this baud rate generator model? Let me open it. So in this baud rate generator model, I'm going to wait up to the divisor. And if this particular count has reached this particular value, then I'm going to make the stick is equal to 1. Now, whenever the stick is made to 1, then what are we going to do? Then if baud tick is equal to 1, then we are going to check for the synchronizer. That means if my input is equal to 0, yes, if the input is equal to 0, then I'm moving to the data state. This is what I'm going to do. Okay. Now, if I've entered into data state, so in the data state, again, I'm waiting for the baud tick because I need to wait for that many number of cycles. Now, here, tick count, if it is equal to 15, then tick count will be equal to 0. And I'm basically, whatever the data which was sent to me, that I'm going to store it into my RX underscore byte. Okay. So this bit index initially it will be equal to 0. So bit index value is initially equal to 0. and this will be incremented one by one. So initially Rx underscore byte will be equal to 0. Now we have something known as tick count is equal to 15. So let us try to understand about this particular what do you mean by tick count and all. 1 second, give me 1 second. Before that, I was getting a call. Yeah. Now, where are we discussing over here? Hmm, we were discussing about our UART RX, right? Now, in the UART RX, we are basically discussing about this particular start bit we have discussed it, and we have moved into this particular data bit. Okay. Now, in the data, we are basically waiting for this Baud tick Baud tick to be equal to 1. That means we have completed our 5200 cycles. And we are also
Excuse
waiting.
me, sir.
Yeah.
Sir, your screen is not visible.
Yeah. Thank you for letting me know. Now is it visible? Now, one more important point over here to be noted that we have measured just now is the divisor value. So divisor which is equal to clock frequency divided by baud rate into 16. So this is what we have done. Now, let us try to understand what is this clock frequency divided by baud rate into 16. So basically, we are trying to divide this. If we are going to have clock frequency as 50 megahertz and the baud rate to be 9600, I'm going to get 5208 cycles. And if you divide it by 16, this is a value you're going to get 325. So the divisor value is now 325. So that means for every 325 cycles, my baud enable will be equal to 1. So this listen this carefully. This will be very, very interesting to understand. This is nothing but my oversampling factor, and let me try to explain it more clearly. So let me erase this. Now, so what is happening for achieving a baud rate of 9600, I should basically maintain every particular bit. It might be start bit, or it may be data bit, and it may be stop bit, right? Up to D7. I need to maintain every particular bit for how many cycles? 5208 cycles. This should be present for 5208 cycles, and this should be present for 5208 cycles. Like this, every particular bit should be maintained for 5208 cycles. Okay, this is our requirement. And the transmitter is doing that. Okay, now in the receiver side, what are we doing is this particular bit, let me draw it visually. So this particular bit is maintained for 5200 cycles. So on up to 5208 cycles, this particular start bit will be made to 0. Like this, it is made to 0. Okay. Now, this is my transmitter. Transmitter is providing the start bit constant to be 5286. Now, receiver, what it is going to do? Receiver is going to sample the start bit for every how many cycles we have calculated oversampling factor is 325. So for every 325 cycles, we are going to sample it. That means I'm going to have the 325th cycle, I'm going to sample it for once. And again 325th, I'm going to sample it. Like this, 16 times I'm going to sample it same bit. Okay, this is nothing but my oversampling factor. Oversampling factor of 16 is nothing but you're sampling a single bit for 16 number of times. That means for every 325 cycles, you're going to sample. And how many times you're going to sample the same bit? You're going to sample it for 16 times. Not only start bit, you're also going to sample this data bit. How many times you're going to sample it? 16 times you're going to sample it. And how many times you're going to sample your D2? You're going to sample it for 16 number of times. That means for whenever your 325th cycle has been given, you're going to sample it. Like this, you're going to sample it for 16 number of times. Is it clear? What do you mean by oversampling factor? Now, what is it we are going to do? This particular oversampling factor Baud enable. So in the code, if you carefully observe over here, in the code, we have written divisor is equal to clock frequency divided by baud rate into 16. Okay. So that means for every particular 325 cycles, this particular tick will be equal to 1 because count is equal to divisor minus 1. Tick is equal to 1 we have written, right? So that means for every 325 cycles, this tick will be equal to 1. Now, this tick signal is given to your UART RX. Here you can see baud underscore tick is equal to 1. We are going to sample our data. And when are we going to store our data when our tick count is equal to 15? That means after completing entire sampling, because we are sampling it for 16 number of times, right? So that's the reason. Tick count, if it is equal to 15, I'm going to make my tick count is equal to 0 and I'm going to sample the final data. Okay. And if bit index is less than 7, I have total 8 bits of data right now. So here I'm basically writing the logic for basically checking how many bits of data I'm going to have. So if bit count is less than 7, I'm going to increment this. Or else I'm going to make this is equal to 0. That means I have sampled all the particular data and I'm going to stop state. This is the logic which I'm going to write down over here. Okay. Is it clear, guys? Now, next what I'm going to do, next I'm going here, this is my parallel to serial conversion. Sorry, serial to parallel conversion. This is my serial to parallel conversion, which I'm going to have. Next, what I'm going to do, one second, is the screen not visible? Yeah, it's visible. Now, next, what I'm going to do, I'm going to stop state. So again, if my baud tick is equal to 1 and tick count is equal to 15, that means I have sampled all the particular data. Then I'm going to clean up state. And from the cleanup state, I'm going to idle state. So in the stop state, what I'm going to do, I'm going to provide my Rx data is equal to Rx byte, last bit of data, and Rx done is equal to 1. This is what I've done, and I'm entering into my idle state. So this is how I'm going to receive the data from the bridge. Okay. So basically, the bridge has successfully received the data. Now, after, sorry, UART-RX has successfully received the data. Now, receiver, after receiving the data, it is going to give it to something known as command decoder. So someone is in unmute state. Can you mute yourself, Karthik? Yeah, thank you. So after UART receiver has received a particular byte of data, what it is going to do, it is going to give it to your command decoder. So command decoder, it is going to have clock and reset and RX underscore done and RX underscore data as its input. So RX underscore done and RX underscore data, we are getting it from the UART receiver itself. Now, command decoder output is brightness update, brightness value, LED select update, LED index, mode value. What is this? I will let you know. So over here, this is my receiver, UART receiver. It has converted into a parallel data and it is going to give this particular 8 bits of data to the command decoder. Now command decoder, it is going to decode it. So what it is going to do? So it has the outputs as brightness underscore update, brightness underscore value, LED underscore index, LED underscore update, mode underscore value, mode underscore update. That means if I'm going to update the brightness value, I'm going to tell that I have updated the brightness. If I'm going to update the index value, that means I'm going to tell that I have updated the LED select. And if I'm going to update the mode value, I'm going to say that I have updated the mode. Like this, I'm going to say. So these are just for your single cycle pulses. Okay. Now I'm going to have command underscore brightness as 00, command underscore select as 01, mode is equal to 10. Why I'm taking this? Just now in the previous slides only we have discussed that MSB bits, if it is equal to 00, it is brightness, 01 it is LED select, 10 it is nothing but mode. Okay. Now command underscore type, as I've said you, I'm going to get it from the MSB bits, and command underscore payload is the remaining 6 bits of data. When I'm discussing about the byte format of this particular LED controller, I have told you that this is the byte format. Now, if reset is applied, all this particular will be equal to 0, and by default, this values will be equal to 0. Now, if Rx underscore done, that means UART receiver has successfully converted the parallel serial to parallel conversion, and it is if it has sent me the data, then Rx underscore done will be equal to 1, and depending upon my command type. So, if my command type is command brightness, I'm going to update my brightness value as command underscore payload comma 2-tick binary 00. Why I'm doing this? So I have told you basically I'm going to have this particular brightness value to be 6 bits. So in the frame, the 2 bits are for the mode selection, and remaining 6 bits, 1, 2, 3, 4, 5, 6. This particular 6 bits are used for my brightness value. But I need to have to multiply it by 4 for getting the 255 value. Just now we have discussed it. That. So how to multiply it by 2? I am just left shifting by 2 bits. This is nothing but my left shifting by 2 bits, so that I am basically multiplying it by 4. Okay. So whatever the brightness value I've got, that I'm multiplying by 4 just by left shifting. And I'm updating it in my brightness value, and I'm making this brightness update is equal to 1. Let's say if my command type is command LED select, then LED index will be given from command underscore payload 2 down to 0. So I've told you, right? A command underscore, let me show you. For LED, I'm going to use 3 bits. That is what I'm storing, 2 down to 0. And command underscore mode, I'm going to have 1 down to 0. So you can see for mode, you are going to use 2 bits. So like this, from the UART receiver, I'm storing depending upon what kind of, depending upon what type of command it is, I'm basically storing that particular value inside this particular values. Okay. And I'm ending this particular model. Okay. Is it clear, guys? How I'm basically receiving the data from the UART receiver, and I'm basically decoding them. Okay. So after UART receiver has decoded this particular values, it is going to basically tell to the LED controller. So where is my LED controller? Let me show you the LED controller. Now LED controller is going to get the commands from my command decoder, and it is going to come to know this particular values. So clock and reset are given, and new underscore data. So command decoder, it is going to give the data to my this particular thing. And here Rx underscore data is given to this LED controller from the command decoder. And whatever we are going to have, we are going to basically control it via this LED underscore out. And here I'm going to have something known as duty cycle, which will be used for my brightness. And next is PWM underscore count. So let me show you where I'm going to use it. Now, if my reset is applied, my duty cycle will be equal to 0, and new underscore data is being given. Then I'm basically storing whatever the command decoder, which it has sent the data into my duty cycle. Now, what I'm going to do at passage of clock, my PWM count variable will be equal to 0, and LED count will also be equal to 0. Now, PWM count will be incremented, and my LED out will be equal to 1 whenever your PW count is less than your duty cycle. So what is this means? So let me show you this duty cycle once. So this is your duty cycle, and initially this will be equal to 0. Now, duty cycle value, you are going to give it to Rx underscore data via this Rx underscore data. So this is basically for adjusting your brightness. Let's say suppose, okay, how actually you are going to adjust your particular LED? On what basis you are going to adjust your LED? So basically, we are going to provide the voltage or we are going to not provide the voltage. If you are going to provide the voltage, then LED will be on. And if you're not going to provide the voltage, LED will be off, right? That is what we are going to do over here. Now, let's say suppose I'm going to decide the brightness of my LED depending upon the duty cycle of my voltage. Let's say if I want to have 0% LED brightness, then what I'm going to do, I'm going to make my duty cycle is equal to 0. Then that means my voltage is not at all given. Let's say suppose if I want 100% brightness, then I'm going to give their duty cycle as 100%. Okay. Duty cycle 100% is nothing but it is on forever. Okay. And let's say duty cycle is equal to 50 percentage brightness, then it will be on for half time period and it will be off for another half time period. That is what we are going to do over here. So I have took a counter which is nothing but PWM underscore counter. This will be incrementing, and when this is less than the duty cycle, LED underscore out will be equal to 1. And if it has reached the duty cycle, LED underscore out will be equal to 0. So this is the logic which we have written for basically controlling my brightness of my LED. Okay. Yes. So this is how we are going to control a particular UART, I mean the LED using this particular UART frame. Okay. Yes. So if you're having any particular doubts or any other queries, you can discuss with me or else we can wrap up your session. Okay.